Welcome back everyone. So today I brought another problem from mechanics and mostly it is concept of rotational mechanics. This is a problem from IPHO 2014 paper. So I hope you'll enjoy it. Let me read out the problem first. A small puck of mass M is carefully placed onto the inner surface of the thin cylinder of mass M and of radius r. Initially, the cylinder rests on the horizontal plane and the puck is located at the height r above the plane as shown in the figure on left. Find the interaction force F between the puck and the cylinder at the moment when the puck passes the lowest point of its trajectory. Assume that friction between the puck and the inner surface of the cylinder is absent and the cylinder moves on the plane without slipping. The free fall acceleration is g as it is known, self-understood I guess. Okay, so let me first draw the situation when the puck will be at its lowest point, and I have shown it here that I have assumed at that instant the center of cylinder is having a velocity of v and angular velocity omega as v upon r, as it is having pure rolling, so v equals to r omega relation should be satisfied, and v dash is the velocity of the puck with respect to ground. And on the right hand side I have drawn the figure when I am analyzing the situation with respect to the center of the cylinder. When I am sitting at the center of cylinder, I will observe the velocity of puck as v plus v dash, and I will see it performing a circular motion around a circle of radius capital R, right, about the center of the cylinder. So I can simply apply the Newton's second law that net force will be mass times acceleration. So n minus mg will be m into v plus v dash square upon r, because v plus v dash square upon r is the centripetal acceleration, and mg is its weight, and n is the normal reaction offered by the cylinder to the puck, and we are supposed to find n only. So this is our target, to find n. Here we can see that v and v dash are the two unknown quantities. So throughout the solution we will try to find out v and v dash in known terms, and we will substitute these values in equation 1 so that you can get the required n value. Okay, so that will be our target in the solution. Let's proceed. Now I have shown you the diagram at a general instant, because the puck was released at this point and it will finally reach at this bottommost point. And I have shown you an intermediate situation where the puck is making an angle theta with the vertical line, and these are the two FVDs. This is the FVD of the puck, where n is the normal reaction or the interaction force of the puck with the cylinder, and mg is its weight acting downward. So this component will be n sine theta, this horizontal component. So I can write n sine theta equal to MAP, where AP I have assumed at the acceleration of the puck. Okay, so this will be n sine theta equal to MAP, and this is the FBD of cylinder. This was the FBD of cylinder. So here I have shown the normal reaction or the interaction force between the puck and the cylinder. N dash is the normal reaction offered by the ground to the cylinder. Small f is the frictional force, and capital Mg is its weight, which is acting from its center of mass, right? And AC I have assumed it is acceleration of the center, and alpha as its angular acceleration. And you can easily observe that alpha will be anti-clockwise only because capital N dash and capital Mg will have no contribution towards alpha, only F will have the contribution, frictional force, and that will ensure an anti-clockwise angular acceleration. And again I am writing the force equation in horizontal direction for the cylinder, that is n sine theta minus F equals to MAC, and I am substituting n sine theta value here as MAP, and also I am writing the torque equation for the cylinder, that is F into R, radius of the cylinder, will be I into alpha. I will be obviously capital M into R square, and one R and R gets cancelled, and R alpha we can put as AC, because AC will be also equals to R alpha because pure rolling condition is maintained throughout the process. So from here we will get F equal to MAC, and I'm putting this in this equation. So eventually it will come like this, that MAP will be twice of capital M into AC, and AP is the acceleration of the puck. So I can write it as a differential form in dv prime dt, as v dash is the velocity of the puck in ground frame, I have already assumed. So I can write AP as dv prime dt and AC as dv dt. Now integrating both the sides, we'll get to this relation. Initially both the velocities were 0, I mean v and v prime, and at a general instant it is v and v prime as I have assumed. So this equation 2 is a very important one, because through this equation you can relate v dash and v. So that's the immense helpful equation. Now still v dash and v prime are unknown. We have just related these two, but we'll try to bring v dash and v values in terms of some known quantities. Now we will use energy conservation. Now some of you may argue that if friction is there, how can we conserve energy? But that's a static friction, because the point of contact is having zero velocity at every instant. So the displacement of the point of contact where friction is acting is always zero. So work done by friction is zero, and we can conserve the energy. That is what we do in case of pure rollings. So I think it's very clear to you. So then in energy conservation, I am writing the decrease in potential energy here, that is mgr, because the puck was initially here and finally it will be here. So the decrease in height will be r, and so decrease in potential energy will be mgr, and this decrease in potential energy will compensate to the increase in kinetic energy, and its kinetic energy will be half mv dash squared, that is the kinetic energy of the puck, and half capital M v square is the translational kinetic energy of the cylinder, and this part half I omega square is the rotational kinetic energy of the cylinder. Now I think it's just the calculation from 2, I mean where we have related v dash and v. We'll substitute the v dash value in terms of v, and we'll get this. Now if you proceed, you will get to this one, this v square equals to m square gr upon twice of capital M square plus capital M into small m. Now let's go back to equation 1. We are supposed to put the values of v and v prime here and get our required n value. So I'm just doing this right now, that I have put the v dash values in terms of v first. So now whole thing is in terms of v only, one unknown quantity. Now this there, if we take common v out from this bracket, we'll get v squared term, and this one is the v squared terms. I put the value of v square here, and now I think if each term is a known quantity, I mean capital M, small m, g, capital R. Now just calculation it is. So you do the calculation and you will get this result, that n will be equals to small m into g whole multiplied by 3 plus small m upon capital M, and this is our answer for this question. But I will leave you with one more question related to this problem only. I will ask you to find the radius of curvature of the puck, right? ROC of the puck at its lowest position. So this was not the question asked in IPHO, but I am adding one question here. They only asked you about the interaction forces, but you can find out the radius of curvature also at this instant. So let me know the answer in the comment section, and that's all for today. Thank you, and stay tuned for some more interesting problems.